Swayam Prabha. Digital India. Educated India.
Dear viewers, in this session, I would like to focus upon the various techniques and methods by which data as required by DM can be collected from the ground. Thereafter, this information needs to be converted into the required form for surface analysis. So, let us look at the acquisition of data for digital terrain. Digital terrain data may be acquired by a variety of methods depending on the factors such as location and the size of the area of interest, the purpose of terrain modeling and the technical resources available. The next table, as a matter of fact, provides us a brief information regarding the various methods of acquiring digital terrain data along with the appropriate technology, the accuracy with which the data can be collected, the type of the extent of area coverage and the typical examples. So, if we are having ground surveying based methods of data collection, well, the technology that can be used is total or semi-total stations. The accuracy by this particular method of data collection is very high. However, the area coverage is limited and is useful for specific sites. The typical applications could be small area site planning and design. The next method is photogrammetry, wherein one may use stereo plotting machines with or without correlators. The accuracy is high if we use spot elevations to prepare the DAM, or it could be low if the contours are being used. Well, this is useful for large area projects, specifically in rough terrain. The typical applications could be large engineering projects such as dams, reservoirs, highways, open cast mines. The third methodology of data collection could be cartography, that is with the help of existing maps. In this, the data may be manually digitized, or we can use certain semi automated line following procedures, or we can go in for scanning of the information. The accuracy by this particular method is naturally low. However, it has a very distinct advantage that it provides a large area coverage, that is at the level of nationwide at small scales. Well, the typical applications of this type of method input could be for aircraft flight simulation, landscape, visualization, landform studies, military battle simulations. Generally speaking, ground surveying methods are most suitable for large scale terrain modeling for engineering and mining applications. At smaller scales covering greater geographic areas, photogrammetric methods are always used. So, let us look at the next aspect, and that is terrain data collection. This could be achieved by field surveying methods, by photogrammetry, by digitizing existing maps. Field surveying methods of data collection. Conventionally, terrain data is obtained in field surveying by grid leveling and stadia tachometry. These methods have been replaced by new generation of surveying equipments such as electronic tachymeter and the global positioning system or GPS. An electronic tachymeter is an equipment or an instrument that is capable of electronically measuring both angles and distances and performing basic computations, that is reducing slope distances to the horizontal and determining coordinates from bearings and distances. Some electronic tachometers are also equipped with an internal memory or an external data recorder for temporary storage of data. Because of the ability of this category of instruments to perform multiple functions in the field, they are sometimes referred to as total stations. In this particular slide, one can see the total station, which is nothing but a theodolite which has the capability to record all the information electronically, and based on some of the inbuilt functions available, the surveyor can compute directly the coordinates of the point of observation. The next method of data acquisition through field surveying is through GPS. GPS is a satellite based surveying system that allows the user to obtain highly accurate digital terrain data electronically. There are two basic methods of field measurements using GPS, that is static and differential. Static GPS survey is used to determine positions of survey control points in areas where the geodetic control is lacking or unreliable. It is also used to measure the distance between the 2 points accurately. Distance measurements require the use of 2 or more dual frequency GPS receivers that record measurements of the GPS satellites simultaneously for about 6 hours. Static GPS surveying is used mainly for geodetic control and the measuring of the national and international networks. It is not intended for ordinary digital terrain data acquisition. Differential GPS surveying makes use of existing or newly established control points as a reference to determine the positions and heights of ground points. A kinematic GPS surveying method is used to make measurements along a line in open areas. Stop and go GPS surveying is used to survey detailed points that are relatively close together in an open area. A real-time GPS surveying configuration is made up of a reference station and one or more roving units. The reference station includes a GPS receiver, a controller and a radio modem. The next method could be photogrammetry. Photogrammetric methods are used when the terrain of interest is too extensive or too rugged for field surveying methods to be applied practically. With the appropriate choice of photographic scale, flying height, base to height ratio and equipment, photogrammetry can be used for acquisition of digital terrain data over a wide range of map scales and degrees of accuracy. So, digital terrain data may be obtained by any of these conventional photogrammetric methods using an analog stereo plotter equipped with encoders, using an analytical plotter and using a digital photogrammetric technique. So, let us look at data collection using a analog stereo plotter. This is an conventional photogrammetric method to obtain 3D data from aerial photographs. 3D coordinates of elevation points in the stereo model may be digitized by equipping the stereo plotter with linear and rotatory encoders. data collection using an analytical plotter. An analytical plotter uses a mathematical or a numerical solution using photogrammetric measurements. Using the x, y and z terrain coordinates of a point measured by the operator, the main processor of the analytical plotter computes the corresponding photographic coordinates of the same point on each photograph of the stereo pair in real time and moves the positions of the photographs accordingly, so that the measured points can be viewed stereoscopically, that is in 3 dimensions. The next technique could be using digital photogrammetry. Digital photogrammetry is a technique that has changed the methods of acquiring topographical data from aerial photographs. Instead of using conventional photographic diapositives, digital photogrammetry uses digital images obtained either by scanning aerial photographs at extremely high resolution, that is at about 1200 dpi or higher, and by the use of remote sensing imaging systems. A digital photogrammetric system includes the hardware and software that makes up the digital photogrammetric workstation, or in short it is known as DPWS, and the peripheral devices for data conversion between the analog and digital formats. The third method of data collection could be by digitizing the existing maps. Existing topographic maps contain a wealth of terrain data that may be used for digital terrain modeling. As the acquisition of digital terrain data by field surveys and photogrammetric methods is a costly and time consuming, thus digitizing existing maps has often been as a practical alternative. Digital terrain data for a large area may be obtained within a relatively short time and at modest cost. At present, the most digital terrain data collected at national or state or provincial levels have been converted from existing topographic maps rather than acquiring by carrying out new field or photogrammetric surveys. In this particular figure, one can see the manner in which the data from a contour map is converted into a DEM. The original contour map is digitized, and here the digitized contours are done with the help of certain sample points which represent a change in the information. Now, depending on the method of data conversion and subsequent generation of DEM, we may have 2 different paths before we arrive to the same path as shown in this particular figure. So, if the data is kept in vector form and it is taken ahead, it can be converted into a process of triangulation into a tin model. If random to grid interpolation is adopted, then in that case we get a digital elevation model which is raster in nature. Based on the method of converting the ground data into DEM, we can have different types of outputs which can be made available. For example, we can get surface generations, we can get color contour generation, we can get a visualization of the ground as it exists. One thing which is very important in DEM data collection, and that is data sampling. Points on a terrain surface can be viewed in various ways from the differing viewpoints inherent in subjects such as statistics, geometric, topography, science, etc. Therefore, different sampling methods can be assigned and evaluated according to each of these different viewpoints as follows: statistic based sampling, geometry based sampling and feature based sampling. From the theoretical point of view, a point on the terrain is a zero dimension, that is without using size, while a terrain surface comprises an infinite number of points. If full information about the geometry of terrain surface is acquired, it is necessary to measure an infinite number of points. This means it is impossible to obtain full information from the terrain surfaces. However, in practice, a point measured on a surface represents the height over an area of certain area. Therefore, it is possible to use a set of finite points to represent the surfaces. Indeed, in most cases, full or complete information about the terrain surface is not required for a specific DTM project, so that it is necessary only to measure enough data points to represent the surface to the required degree of accuracy and fidelity. Now, let us look at the data sampling techniques on geometry based sampling approaches. From the geometric point of view, a terrain surface can be represented by different geometric patterns, either regular or irregular in nature. The regular pattern can be subdivided into 1D or 2D patterns. If the sampling is conducted with a regular pattern that is only regular in one dimension, then the corresponding method is referred to as a profiling or contouring. A 2D regular pattern could be a square or regular grid, or a series of contiguous equilateral triangles, hexagons or other regularly shaped geometric figures. The next is statistics based sampling. From the statistical point of view, a terrain surface is a population called a sample space, and the sampling can be carried out either randomly or systematically. The population can then be studied by the sample data. In random sampling, any sampled point is selected by a chance mechanism known as chance of selection. The chance of selection may differ from point to point. If the chance is equal to all sampled points, it is referred to as simple random sampling. In systematic sampling, the points are selected in a specifically designed way, each with a chance of 100% probability of being selected. Other possible sampling strategies are stratified sampling and cluster sampling. However, they are not suitable for terrain modeling. Next is feature based sampling. From the point of view of features, a feature surface is composed of a finite number of points, and the information contents of these points may vary with their positions. Therefore, the surface points are classified into two groups, one of which comprises feature specific or FS or surface specific points and lines, while the other comprises of random points. An FS point is a local extreme point on the terrain surface, such as peaks, pits and passes. These points may not only present their own elevation values, but also provide more topographic informations to their surroundings. Peaks are summits of mountains and hills, so they have a set of greater height values around them. That is, the FS points are more important because they not only contain the coordinate information about themselves, but also implicitly represent some information about their surroundings. Thus, FS points represent surface features with higher or more significant information content than the average points. The lines connecting certain types of feature surface points are referred to as feature specific lines, such as ridge lines, course lines, rivers, valleys, ravines, etc., break lines, and so on. In the figure below, we can see some of the typical illustrations of FS points and lines. So, the peak is a FS point and the course line and the ridge lines are the FS lines. Now, let us look at the sampling strategy. Acquisition of terrain data is a sampling process because it is impossible to record each and every point on the earth's surface. There are two approaches to digital terrain data sampling, that is systematic and adaptive. In systematic sampling, elevation points are measured at regularly spaced intervals. The result is a matrix of elevation values that is usually referred to as a DEM. When the adaptive sampling method is used, elevation measurements are made at selective points that are assumed to be representative of the terrain. The result is a collection of irregularly distributed elevation points that must be properly structured before they can be used for further processing. Since the method of triangulation is used to build the spatial framework of storing the elevation values, the data collected by this approach is referred to as a triangulated irregular network, or in short TIN. Now, let us look at the attributes of sampled source data. Sampling is the process of selecting those points that have to be measured in certain positions. The operations can be characterized by two parameters, that is, its distribution and density. Measurement is to determine the x and y coordinate of a point and is concerned with accuracy. Sampling can take place before or after measurement. Sampling after measurement is to select points from a set of measured data points, usually with great density. Therefore, accuracy can be included in the attribute set of the sample data called DTM source data, raw data, or simple source data. Composite sampling and integrated strategy. Another way of sampling is to combine a regular grid sampling with selective sampling, because the former is very efficient in measurement and the latter is very effective in surface representation. Such a combination is referred to as a composite sampling. In this way, abrupt changes and specific features on the terrain, such as ridges, break line, etc., are sampled effectively, and the value and the feature specific points, that is peaks, passes and hollows, are added to the regular grid sample data. Distribution of sample data. The distribution of sample data is usually specified by the terms of location and pattern. The location is defined in terms of two positional coordinates, that is longitude and latitude in a geographical coordinate system or easting and northing in the grid coordinate system. Regarding pattern, a variety of these are available for selection, such as regular or rectangular grids. These patterns can be classified in different ways. The figure below shows one such classification. Here we can see how data patterns can be classified as 2D regular, 1D regular, then it could be special, string or random, and based on the type of pattern that we are having, say 2D, it could yield a regular grid or it could yield a square grid. 1D regular data pattern could yield a profile or the contour of the given region. Then we may have special type of data patterns, for example, regular triangles or hexagon. Strings information which provide the details regarding the break and the feature lines, and random could be very important points and its representatives. The next approach could be selective sampling, that is very important points and other points. Selective sampling mimics field surveying in a way that all important points, or in short VIPs, are selected, thereby ensuring that data are reasonably comprehensive in coverage. In addition, some others are selected to make the sample data have a certain density. This method has the distinct advantage that the fewer the points can represent the surface with high fidelity. Sampling with one dimension fixed, that is contouring and profiling. In this approach, the height is kept fixed and the data is sampled along the contour line and recorded in digital form. These points can be recorded in a very selective manner. If the data is sampled at fixed point in the x direction, then the information collected is in the y and z direction, resulting into a profile. Sampling with two dimensional fixed, regular grids and progressive sampling. Regular grid sampling ensures that the data points are obtained in the form of regular grids. This can be achieved by setting the fixed intervals in both x and y directions to form the plane grid. Then all points on the grid nodes are measured. In this approach, additional data is required to ensure that all slope discontinuities are detected and that changes in the topography are represented in an adequate manner. To solve the problem of data redundancy in regular grid sampling, Makarovic designed a modified strategy which is called as the progressive sampling. In this procedure, the sampling is carried out in a grid pattern whose interval changes progressively from coarse to fine over an area. The next data set is the regular 2D data. The regular 2D data are produced by means of regular grid or progressive sampling. The resulting pattern could be a triangular grid, a square grid or a hierarchical, that is progressive structuring of these two. The square grid is most commonly used. The hierarchical data structure data sampled by means of progressive sampling can be decomposed into a normal square grid. Data that are regular in one dimension and produced by sampling with one dimension fixed x, y or z, that is such a pattern is generated by using contours and profiling. Irregular patterns. Irregular patterns generally be classified into three groups, that is random, cluster and string data. By random data, we mean that the measured points are located randomly, that is, not in any specific form. In clustered data, the measured points are clustered, which is often the case in geology. String data are not located in a regular pattern, yet they follow certain features such as a break line. The data sets that are sampled along rivers, break lines or feature lines all belong to this pattern. Actually, it is not an independent pattern, but rather a supplemental one that is feature specific. For example, the pattern of the data resulting from composite sampling is usually a combination of string data with regular grid data. Now, let us look at the density of sampled source points. Density is another attribute of the sampled data. It can be specified by measures like the distance between 2 points, the number of points per unit area and the cutoff frequency. The distance between two sampled points is usually referred to as the sampling interval or distance or spacing. If the sampling interval varies with positions, then an average value can be used. This measure is specified by a number with a unit, for example, the number of points per unit area. For example, it could be 500 points per square kilometers. Having had a look at the data that we have collected from various sources, in order to see that the data does not have too much of error, we need to look at the quality and the standards that digital terrain data must have. Quality and standards are key considerations in the digital terrain data acquisition. The object of quality control and enforcement of standards is to ensure that the errors inherent in the data sets are within an acceptable limit and quantifiable, so that they may be used with confidence. The quality and the standards of digital terrain data may be explained from three perspectives. First, factor governing digital terrain data quality, quality control criterions and procedures during data acquisition, and third is DEM data standards. So, let us look at each of them one by one. First is factors governing the quality of digital terrain data. The quality of digital terrain data is affected by a number of interrelated factors. These are methods of data acquisition and model production, types of source data, nature of terrain, method of interpolation. So, let us look at method of data acquisition and model production. Of the different methods of digital terrain data acquisition described in the previous sections, field surveying methods produce digital terrain data of the highest quality, followed by photogrammetric methods and then cartographic map digitization. Large DEMs data set are usually produced using different methods and with different types of source data. Such data sets probably contain all kinds of inherent errors that may have occurred and accumulated during the acquisition of the source data sets. Then is type of source data. Similar production methods, different types of source data may generate different digital terrain data of very different qualities. Next is nature of terrain. Image correlation algorithms often exhibit the poor fit and hence lowest accuracies in forested areas because of the lack of clearly defined topographic features such as roads, buildings and vegetation boundaries. Method of interpolation. Different methods of interpolation used to generate DEMs and TINs employ different algorithms. They may or may not include the mechanism that performs drainage enforcement to overcome the problem of spurious sinks and maintain a connected drainage pattern. As a result, the quality of the DEMs and the TINs produced by different methods of interpolation may vary considerably. Quality control and criteria and procedures. Different organizations have developed different criteria and procedures for quality control in digital terrain data accuracy. The quality control system at the USGS, for example, includes the following principal items. These are statistical accuracy tests, data editing, verification of logical and physical formats, and visual inspection. Statistical accuracy tests. This includes testing of the general accuracy of the individual data sets to ensure compliance with the mapping specifications. All USGS DMs are tested and assigned a vertical root mean square error. This is computed using a minimum of 28 test points per DEM. Out of these test points, 20 are selected from the interior points and 8 from edge points. The edge points are used for edge testing, which evaluates how well elevation values along adjacent DEM matches the edge. Data editing. The objective of editing is to ensure the conformance of the data to criteria governing constraints to data for water bodies, that is type, size, elevation, hydrography, that is drainage, lakes, swamps and shorelines, and slopes, that is natural breakpoints. Verification of logical and physical formats of data files. The logical and the physical formats of all DEM data are validated by a special program as a part of the database entry procedure. Then is visual inspection. Using a computer program called DEM editing system, that is DES, this process aims at identifying blunders such as irregularly gridded data and wrongly tagging of elevation values, which may require elevation with original source data. Then we come to DEM data standards. USGS DEMs are classified into 3 levels according to data quality. Data sets that fail to satisfy these standards for classification are not normally released for distribution. The specifications for the 3 levels of classifications are as follows: level 1, level 2 and level 3. So, let us look at level 1. This represents the lowest level and includes 7.5 minutes DEMs and an equivalent derived from photogrammetric stereo profiling or image correlation using high altitude aerial photograph. The desired accuracy standard is a vertical RMS of 7 meters or less, with 15 meters as the maximum permissible. A 7.5 minute DEM at this level has an absolute elevation error tolerance of 50 meters for blunders for any given node when compared to the measured elevation. The next is level 2. Here the DMs have been processed or smoothened for consistency and edited to remove identifiable systematic errors. These include elevation data sets derived from hypsographic and hydrographic data digitization, either by photogrammetry or by map digitization that have passed the review process on a DM editing system. An RMSE of 1/2 contour interval is the maximum permissible error tolerance with no errors greater than 1 contour interval. The next level is level 3. The DMs, which represents the highest accuracy of all the 3 levels, are derived from digital line graphs or DLG data using selected elements from both hypsography, that is contours and spot heights, and hydrography, that is lakes, shorelines and drainages. Ridge lines and hypsographic effects of major transportation features are also included in the data. An RMSE of 1/3 of the contour interval is the maximum permissible error tolerance with no error greater than 2/3 of the contour interval. In the next session, I would focus on the methods of surface representation by a DEM. Thank you.